Well, hello everyone and welcome. Today I want to start talking about quadratics, and that's a big part. So get something to write with because I'm going to do some thinking. Hopefully I'll be thinking out loud. Want to reproduce in your mind the same thoughts after me, and then you should make a record of them. So get something to write with, either the note guide or some graph paper and things like that. But let's get started. All right, so before we do quadratics, let's just do a little bit of review. The most basic function would be something like f of x is equal to c, where c is just some kind of a number. And so let me just do just a simple one. What if I said f of x is equal to 3, right? There's no variable there. That would be the same thing as y is equal to 3, which means all y's are 3. Meaning that every single point that's a solution there is has got a y value of 3. So that would just be a horizontal line. Okay, this is your most basic function. This is called obviously the constant function. Why is that? Because there's no variable. It doesn't ever change. The output value, the y value, the function value, because all of those mean the same thing, is constant. It doesn't change. I guess theoretically, you could do this. You could say that this is f of x is equal to c x to the 0. Because what does the 0 exponent means? It means none of that thing, but it doesn't mean 0. It means I still have a c. So this would be like f of x is equal to 3x to the 0, and y is equal to 3x to the 0. But normally you don't write that. But I'm just pointing that out. Okay? So that would be your basic constant function. The next function up in complexity, if you want to call it that, is f of x is just simply equal to x. And what's the exponent on x? That would be 1. It's x to the first. And so as a graph, maybe this one would be the same thing as y is equal to x, which basically says everything that x is, y is also that thing. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. And, the negatives as well. And so we get this straight line kind of a function here that does have a slope other than 0. So that is your parent function for a variable with an exponent of 1. Now, we've done some things with these before with variations of that. You can change the slope, because this is in standard form, it would be y is equal to mx plus b. In the one we graphed here, the slope is 1x, and then what's the b value? That would be 0. Okay. Now, if I didn't have an x, it would just be y is equal to b, which is the one that we just did over there, except we called it c. It doesn't matter really what you call it. It's just a constant thing. But we can shift the graphs up, and make them look like this. We can change the slope and make it steeper. And so we did a lot of that previously. That would be a linear function. The highest degree on x is to the first. The degree means the exponent. So now let's do that higher up one more. That was an awkward way to say that. Let's do it to an exponent of 2. Okay, so here we go. This is the quadratic function. Y is equal to x squared, the simplest one. And so let's just do really kind of a table of values here, and then we'll plot some points. And then we'll see what the graph of this thing looks like. So this will be x and this will be y. And of course, the easiest thing to do is to pick 0. So when x is 0, what's y? Well, y, remember, is equal to x squared. So in this case, y is equal to 0 squared. That's 0. So 0, 0 is a point. I'm doing them in a table vertically because I want you to see the x and y values side by side, because then they correspond nice and neat to some points, and you can just go plot them. Okay. How about when x is 1? Well, what is y? Y is equal to 1 squared. That's also 1. How about 2? Y is equal to 2 squared. That's 4. Keep going here. Oops, don't want to show that yet. Keep going here. How about negative 1? Y then will be equal to negative 1 quantity squared. It's a group. That's still positive 1. And how about negative 2? Still positive 4. If we did 3, it would be 9. And if we did negative 3, it would be still positive 9. So if I come over here and I graph these points now, I'm going to focus kind of on the graph. 0, 0 is there. 1, 1 is here. 2, 4 jumps up a bit. And then 3, 9 would be like way up here. But if I go to the left, negative 1, positive 1. And if I go to the left again, negative 2, positive 4. And if I go to the left, negative 3, positive 9. And so I get this very smooth curve. It should be smooth. Don't make it like pointy, connect the dots sort of things. And it comes up like this. Continually getting steeper and steeper and steeper. Well, I really missed that point right there. That's not right at all. Like way up here. So steeper and steeper and steeper and steeper. It looks like that. Okay. So let's now discuss some of the properties. Okay. This is now the general form of a quadratic function. X is or f of x, which is the function name, is equal to ax squared plus bx plus c, where a, b, and c are just numbers. So for the one that we had, y is equal to, or f of x is equal to x squared, the a value was a 1, and then the b was 0, and then the c was 0. So all we had was this one right here. That was the one that we just graphed. Okay, but it could be other things. Your b and c don't have to be equal to 0. For example, I could say there's another function maybe where f of x is equal to 5x squared minus 4x plus 7. And in this case, a would be 5. B would be negative 4. C would be equal to 7. Okay, so these are quadratic. They're quadratic because the highest exponent of any variable is 2. And you can change the order of these provided that the sign goes with the correct coefficient, but general form says you go down in degree. The first exponent you have on your variable is 2, and then you go down in whole number steps. So what's the exponent on the bx term? Well, that would be an exponent of 1. And then cx to the, again, 0. So it counts down of 2, 1, and then 0 for your exponents. The name of this shape, it's called the parabola. That shape right there is called the parabola. It can get skinnier, it can get wider, it can go upside down, it can even go sideways for that shape. But it can't go sideways and still be a function of x, but we'll get into that a little bit later. All right, so now the y-intercept. The y-intercept is where the graph crosses the x-axis. The y-intercept on this one is going to be right here. But as we did with lines, the y-intercept is the location where x equals 0. Now, if I come back and look here at this function, and I say that y is equal to ax squared plus bx plus c, but I put 0 in for x, let's see what we get. Y is equal to a times 0 squared plus b times 0 plus c. Don't the things times 0 just drop out? And so the y-intercept is always going to be the y value equal to c, wherever it may be. Remember, it's a point, though. It's also where x is equal to 0. So it will be the point. The y-intercept would be the point 0, c, when it's written in standard form. Okay. Now, there's also an axis of symmetry. If you will look here, there is actually a line that splits the shape of the parabola into two kind of mirror images. That line right here happens to be the y-axis. It doesn't always have to be the y-axis, but there's a line of symmetry through here. And maybe I'll even do that with a dashed red line. It's not a solution line or anything like that. It's just like an imaginary property line or something like that. That would be your axis of symmetry. Okay. Now, before I get into telling you details on the axis of symmetry, I want you to tell you the most important point about a parabola, and that's the point that is called the vertex. Okay, the vertex is this turnaround location right down there. That's the vertex. The axis of symmetry always goes through the vertex. And so now let's get into it. The vertex as a point has got some special labels. The vertex is always the point H and K, where H is simply the X value of that turnaround point, and the K value is the Y value of that turnaround point. H and K are, they're not really variables, they're not variables, they're values, but they're special values, and different shapes of different functions have different special points, like a circle has a center, or something like that. And so H and K are oftentimes used to represent those special points. They're not variables, but they are special locations on the graph that we're talking about. And the most important point on a parabola is the vertex. Now, the X value of the vertex, which is the H, so the H value is equal to, back up here to the general form. Oops, I thought it was the latest. Back up here to the general form right here. H is equal to negative b over 2a. You should memorize that. Negative b over 2a. And then whatever you do to find the k value is simply equal to the function evaluated at h. Find the x value of the vertex and then plug it into the formula or the equation, and you'll then find the y value of the vertex. Okay, so now when we finally do the axis of symmetry now, since this point right down here in the bottom is HK, and this vertex is the axis of symmetry is a vertical line, the equation of that line is going to be x is equal to h. So the axis of symmetry is going to be x is equal to h, whatever that vertex value is. Now, I realize that's a whole lot of information, especially if you haven't seen it before. So maybe rewind the video and pause it at certain points to kind of get some of this down. But now let me put it into practice. So example number 1, graph the quadratic function, and there it is. F of x is equal to 4x plus x squared minus 3 by identifying the vertex, the y-intercept, the axis of symmetry, and then plotting 5 points total. All right, so the first thing that I need to do is I need to rewrite it because it's not in general form. Do you see up here that the x squared term is not the first term? It's written out of order, okay? So I need to change the terms around, and I can move the terms around provided that the coefficient goes with it, which includes the negative sign here if I'm going to move this around. So I'm going to rewrite this now as f of x is equal to x squared, because that one should come first, x squared plus 4x minus 3. Okay, now that's in general form. Let me identify my a and my b and my c. My a is equal to 1. That's the coefficient that's out in front of the x squared term, and it's not written. And of course, when you know that when it's not written, it's 1. B is the coefficient on the x term. B is equal to positive 4, and c is equal to negative 3. Okay? Now, the next thing I do is I need to find my vertex. The most important thing I do is find my vertex. So what's the vertex? The vertex is HK. How do I find out what h is? H is equal to negative b over 2a. Oh, I've got an a and a b and a c. So h is equal to negative of b. What's b? Positive 4. Divided by now 2 times 1. So what is h now? What's negative 4 divided by 2? I think that's negative 2. Right? So the x value of my vertex is going to be negative 2. How do I find the y value of the vertex? Well, I do f of negative 2. I plug it into the equation, and then that tells me the y value. So what's f of negative 2? Well, that's going to be, I'm going to use the one that I did up here. That's going to be negative 2 squared plus 4 times negative 2 minus 3. So f of negative 2 is equal to, okay, so that's going to be positive 4 minus 8. Positive 4 minus 8. That's negative 4 minus 3 more. I'm getting a y value of negative 7. Is that what you get? Negative 2, negative 7. Okay, let me plot that point. Negative 2, do I have enough room? I think I do. 1, 2, 3, 4, 5, 6, 7. Wow, the vertex is way down there. Okay, now, what's the y-intercept? Well, remember I said the y-intercept is just the c value. So the c value here, when I have it in standard form, the c value is just going to be negative 3. Because that's what I get when I put 0 in for x. X would be 0. What's the y value? Negative 3. So 0, 1, 2, 3 right here. I got that. So now I got 2 points. But wait a minute. I've also got an axis of symmetry. Doesn't the axis of symmetry go through the vertex? Yes, it does. And the axis of symmetry is always going to be x is equal to the h value. So that's going to be x is equal to, what was my h value? Negative 2. Now, this is a vertical line because all x's then are negative 2. It's not a solution to the function, right? So that's why I'm doing it in blue rather than in red. So I've got a little axis of symmetry here, a mirror, if you want to think of it that way, that allows me to kind of understand the shape of the graph. And I did that there kind of in blue. So it's not part of the solution, but it is something that helps you see the structure. Now, think about this. All right, so if I've got a solution point over here, which is 2 units, 1, 2, to the right on the axis of symmetry, don't I also have a mirror image point, 1, 2 on the left? I do. So I have a point then that's right here, also on the graph. Nice. And what is that? That is x is equal to negative 4. I bet you $1 if you put in negative 4 to the equation, you would get the same y value, which would be negative 3. But don't ever bet when I say let's bet, because I never bet if I don't know that it's true. So there we go. Was that all the, yeah, that's all the pieces I had here, but now we need 5 points total. Well, I've only got 3. So I need to do a couple more. The ones that I want to do are the ones right and left of the vertex. Here's where you want to find your points. You want to look at your vertex, and then you want to go 1 unit to the right, and 2 units to the right, and 3 units to the right, and then that gives you the same points, the same y values as if you'd have gone to the left. So I see that I've got a vertex value of negative 2, and I have a intercept value of 0. What's in between those? Wouldn't that be y or x is equal to negative 1? So let me do now kind of a separate little thing here. Let's say x is equal to negative 1. What's y? And again, I'm going to plug it back up in here into the function. So that's going to be equal to f of negative 1. I should have given myself more room to work here. I'm a little bit tight. So that's going to be negative 1 squared plus 4 times negative 1 minus 3. It should be a value that's in between this y value, which is negative 3, and this y value, which is negative 7. It's got to be. It should be somewhere in the middle here. So I'm expecting a value that's between negative 3 and negative 7. So f of negative 1 is equal to, what's that? It's going to be positive 1 minus 4. That's minus 3, and then minus 3 more, I'm getting negative 6. So I'm going to use the point negative 1, negative 6, which should be that point right there. And then because of symmetry, I've also got that point right there. Hey, I got 5. Maybe I should even just do one more, like x is equal to 1 or something. But I think you get the idea. So smooth curve. Don't make this a sharp little square thing. Okay, it's not a spear. It needs to be a smooth curve. So down at the bottom here, rounded, and then it comes up and continually up and so forth. Ooh, it's a little awkward here. And again, I appreciate left-handed people because I know what you feel like right at this moment. There we go. Okay, that should be then the shape of that graph. What did we do? I wrote it in standard form, or general form. Y is equal to ax squared plus bx plus c. Okay, and then I identified my a, b, and my c. Then I came through here and I found the vertex by finding the h value by using negative b over 2a. And then I took the x value of the vertex, which is the h, and I plugged it into the function to get the y value. And then I plotted the vertex point. Okay. Then I plotted the y-intercept, which didn't really require any computation. That was this point over here. But then because of the axis of symmetry, I can automatically find another point right there. And then I just go to the left or to the right of the vertex and find some other y values, and I start to see the shape, and then I connect them with a smooth curve. It needs to be pretty. Okay, so now, next one, minimums and maximums. So what if I were to graph y is equal to negative x squared? What would that look like? Okay, so let's see here. Let me just do a table of values, x and y. Let x be 0. What's negative of 0 squared? Well, 0 squared is 0, and then the negative of that doesn't make any sense. Does 0 have a sign? It doesn't. 0 doesn't have a sign because 0 is the location that determines the sign of everything else. To the right, it's positive. To the left, it's negative. 0 doesn't have a sign. So if I were to say, what is the opposite of positive? You might say negative. But maybe it's non-positive because 0 is not negative. Or maybe if I said, what do you call the numbers that are not positive? You can't say negative because 0 is an example of a number that's not positive, but it isn't negative. That's interesting. So let's now do 1. What is the y value? So it's going to be negative of 1 squared. Notice that the negative's outside of the parenthesis. This is not negative x quantity squared. No. Okay. The base is not negative. If you wanted to be really, really technical, you can rewrite it like this. Okay. It's the negative of x squared. It's not the square of negative x. Be careful with that. All right, so that's going to be then negative 1. How about 2? That would be negative of 2 squared. Wouldn't that be negative 4? Okay. How about negative 1? Oh boy, what if I do negative of negative 1 squared? Well, if I do the negative 1 as the base and now square it, that's positive 1. And then negative, oh, I'm still over here with negative 1. My phone's buzzing, they'll have to wait. And then negative 2 would also be negative 4. So if I plot these points now over here, I get this interesting thing. I get a vertex there and there, but then points here and here, and then here and here. So I get a graph that actually is a parabola, but it's an interesting one. It opens down. So here's a general rule. A quadratic function can either open up or it can open down. Let's talk about them for a second. For one that opens down, because I'll go ahead and use the one that I have right here. For the one that opens down, this point, as always, is the vertex. But this is a maximum value. And by maximum, I mean the y value. Isn't that a high point, like a hill, like a mountain? Okay, so here the y value is negative, and it's getting smaller and smaller and smaller as I go up the graph. Here, right at the vertex, that's the highest y value that you're going to get, because afterwards it turns around, and then it goes down again. So this parabola has a maximum value, and it's the y value. We're not talking about the x value. The x can go left and right kind of forever, but the y value has a maximum. There's kind of like a top to this graph. It really doesn't have a bottom. The bottom goes on forever. But it's got a top, which means it's got a maximum value. Okay, good. Now, what about another parabola? We did one earlier that opened upwards. It had a vertex at 0, 0, but doesn't have to have a vertex there. We saw one that didn't have a vertex there in the previous problem. What if I had a parabola that looked like that? That opens up. Okay, down there, that's the vertex. Is this a high point or a low point? This is a low point. What do you call a low point? A minimum. So the green parabola's got a minimum value and the red one has got a maximum value, and that's determined by which direction they open. How can you look at a equation for a parabola and determine which direction it opens? It's got to do with the leading coefficient. Okay, it's got to do with the a value. This right here, this is y is equal to ax squared. What is a equal to in this situation right here? -1. There you go. That's the thing. The sign. When a is positive, it opens up. And when a is negative, like, it opens down. Okay? Crucial point. So, a quadratic function has a, what do we do first? What did I say? A minimum. Has a minimum y value. Now this is another key idea here. Anytime we talk about the function value, it's always the y value. And I probably shouldn't even write that in there. It should say quadratic function has a minimum value. It always means the y value. Function value is the y value. The output value is the y value. Okay, but I wrote it in there on purpose just so you could have your mind draw attention to it. A quadratic function has a minimum y value if the a, which is the coefficient on the x squared term, minimum if a is greater than 0. Because if it opens up, it has a minimum, okay? And a maximum y value if a is less than 0. If a is equal to 0, it's not quadratic. It's maybe a line or something like that. Okay? So you can have parabolas that open up and down. How do you tell? The sign on the x squared term tells you. If it's positive, it opens up. If it's negative, it opens down. And that determines whether you have maximums or minimums. Okay, so now let's look at this one here, example number 2. Let's see if I can get it all in here. All right, so consider this function here. Determine whether the function has a minimum or a maximum value and justify. All right, justify means give a mathematical reason why the answer must be true. So I'm looking at this function here, and I notice again it's out of order. Okay, the number one thing you need to do is rewrite it in general form. So f of x is equal to the x squared term has to come first. Notice I circled the sign with it. Negative 4x squared, and then the x part, plus 12x plus 18. So, does it have a minimum or a maximum? Well, a is negative. Does that mean it opens up or it opens down? This means that it opens down, and maybe even draw a little diagram like I did right there of a parabola opens down. Okay, so does it have a maximum then or a minimum? It has a maximum. There's the answer. Why? Because the a value is negative. That's your reason why. One of the principles that you now know is that the sign of the coefficient on the x squared terms, the a value, tells you which direction the parabola opens. Okay, determine the minimum or maximum value. What is it? Give me the number. Remember though, it's the y value. Okay, how do I find the y value? Well, where's the y value found? The y value is found at the vertex, right? The maximum value is always the vertex y value. So my thought is, how do I find the vertex? I need the vertex. Well, I don't start with the y value with the vertex. I start with the x value with the vertex. What's the x value with the vertex? X is equal to h, which was negative b over 2a. Okay, now we're getting someplace. So negative of b. What's b in this situation? Well, b is 12. So negative 12 divided by 2 times the a value. What's the a value? The a value is negative 4. Okay, let me simplify now. So the negatives are going to cancel. I'll do that first. The 12 and the 2 are going to cancel, leaving me a 1 and a 6. But then the 6 and the 4. So in the end, what I'm winding up with is 6 and 4. Both of those are divisible by 2, so 3 over 2. The h value of the vertex is 3/2. Oh no, does that mean like it doesn't work because it's a fraction? No, you just have to, be a mature algebra student and manage fractions. Okay, so here we go. How do you find the y value then? You plug it into the formula. So I'm now going to do f of 3/2. I really should use horizontal fraction bars, but I'm curious about time. All right, so this is now going to be, I'm going to go back over here to the function now, right there. So it's going to be negative, oops, I'm on the laser again, negative 4 times 3/2 squared plus 12 times 3/2 plus 18. Oh boy, I get to deal with fractions. I have to square this one first, correct? So that's going to be equal to negative 4. What's 3/2 squared? 9/4. Oh, that's convenient. Do you see how it's going to simplify out? That's nice. Plus, oh, I can go ahead and simplify this right here. The 2 and the 12 cancel, leaving me a 6 right here. So it's going to be 6 times 3. That's going to be 18. Okay, and then plus 18 again. So now I'm going to come over here, and do you notice that the 4's drop out? Because isn't that 4 over 1? So this winds up being negative 9 plus, what is that, 36? Negative 9 plus 36, or 36 minus 9. I get the y value then of, well, 36 minus 10 is 26. One more put back onto it, because I really shouldn't be taking off 10. I should be taking off 9. 27? I think the maximum value then is going to be 27. Okay, where would you use this? Well, if something's quadratic, one of the most important things is what's the largest thing that it could be, or what's the smallest thing could be. If this was no longer just some kind of generic function, but if this was like, hey, profit. If you're a business person and you're trying to sell a product, you really want to maximize your profit. It's not always true that the more things that you make, the more money that you can get from them, because you may make so many that people don't want to buy it. You've made too many. You can't sell them fast enough. So maybe you make product, and you make money. But there comes a point where it kind of turns around and goes back down. And you want to find that high point, right? And so you want to maximize your profit and be smart about your business in terms of how many things that you make or whatever it is that you do, so that you can find that maximum value then. Because if you make more product but you make less money, like don't make so much. Okay? So maximize your profit. Or if it was a minimum, if it was a parabola that opened up like this, you maybe want to minimize your cost. So find the sweet spot there where you can make your cost, how much money you pay for your supplies or your work or whatever it is. You want to find the minimum value of that. Okay. So now state the domain and the range of the function. The domain is always going to be all real numbers, because your x's and y's can always go left and right forever. But if this is a parabola that has a high point, it has a maximum, as we established here. And what is that maximum value? The maximum value up there, the highest value is 27, which means on the y scale, that's as high as it can go. It means that your y values are this. Your range has got a ceiling. It's got a top. The y values can be equal to 27 or less than. Okay, so that would be your range. Y values are less than or equal to 27. That would be your domain in your range. Okay, now quadratic equations. How is that different than just a quadratic function? A quadratic equation is when the function an O, is equal to a specific value, most oftentimes 0, or you want it to be 0 when you do it. Okay, so standard form of a quadratic equation is going to be ax squared plus bx plus c equals 0. Okay, it's crucial that it's 0. If it's not 0 on the right-hand side, you need to do some algebra to move it across and simplify. Alrighty? So standard form of a quadratic equation, ax squared plus bx plus c equals 0. So now, find the zeros of the function by graphing this. What does it mean, the zeros of the function? It means the x values that make y 0. And I've already gone ahead and graphed it, therefore. I mean, you could do that on your own. We just did how to graph, so I'll leave that for your exercise. By graphing this. So what does it mean to find the zeros of the function? It means the output of 0. So 0 then is equal to x squared minus x minus 6. But remember, wasn't this y is equal to x squared minus x minus 6? What's the question asking, solving by graphing? It's asking you where on the graph is your y value 0. And by where on the graph, I mean the x value. What x value gives you a y value of 0? And you don't really have to do any computations. You can see that there's one right here. What's this x value? Because this is where the y value is 0. The y value isn't 0 right here. The y value isn't 0 right there. The y value isn't 0 right there, but the x value is. The y value isn't 0 right here. The y value is 0 only at 2 places, because here's your axis right there. There's your x-axis, there's your y-axis. And this is your O for origin. I don't think that's a 0. Oops, can't see it. I don't think that's a 0. That's O for origin. But anyway, the y value is 0 on the graph, because remember the graph is the collection of all the solution points. This is just the grid space. This space over here is not the graph. This is the graph. Where's the y 0? There. So what's that x value? -2. And also here, what's that x value? 3. So the solutions then are going to be x, whoops, look at me, I tried to write with the letters. X is equal to -2 and x is equal to 3. There we go. That wasn't hard, was it? So solving solutions of equations by graphing means that you set it equal to 0, you graph the thing that you have, the function, after you have it set equal to 0, and then you find the y-intercepts, and those are your x values. Okay? You've actually got 3 different options when you do this with a quadratic. Okay? A quadratic equation can have one real solution. That's what you get when it only touches but doesn't cross the x-axis. It's only got one location right here where the y value is 0. That's one. It can have 2 real solutions, like when it crosses down here and goes through and then turns around and comes back up. And so there's 2 of these, this one here and this one here. Or it can have no real solutions. Look, where is that y value 0 on that graph? Nowhere. The x value is 0 right here. That's the y-intercept. But where does it cross the y-axis? It doesn't. And so you're going to have quadratic equations that have no solution, because there is no y value that equals 0. So those are your 3 different options. Okay. Now, estimating roots. All right, so sometimes they don't always occur right at integer values. So here's an example. Solve this one by graphing, and notice what it says here. If exact roots cannot be found, state the consecutive integers between which the roots are located. So if I just go to the graph, and here's the function, x squared minus 6x plus 4. If I graph that, here's what it looks like. If I graph that, I'm looking for the x value where the y is 0. That's here and here. But it doesn't cross right on grid lines. You're going to have to estimate. So what is that x value? Well, okay. Here's 0. Here's 1. What would you estimate this crossing location to be? X equals something between 0 and 1. You probably shouldn't even say x is equal to 0.5, because it's more than halfway. I'm guessing x is equal to 0.7. Maybe you'd have said 0.8. That's reasonable. Maybe you'd have said 0.6. That's reasonable. 0.9 maybe is a little too close. It's got to be more than 0.5 because here's halfway right there, 0.5, and it's, it's to the right of that. What about the other one? So if I go to the right, 1, 2, 3, 4, 5, 6, it's somewhere between 5 and 6. Okay, guaranteed somewhere between 5 and 6. What is it? Can I get any tighter on that? What is it right there? This is 5. This is 6. What would you call that x value? 5 point, don't tell me 5.5. It's less than halfway. 5.1, 5.2. If I'm going to do, what did I say on the other side? 0.7, which is about 3 away. Maybe I'll do 3 of this. Maybe it's 5.3, just to be consistent. Because it is symmetrical. Should be symmetrical with the vertex down here. Just to point out, here's your happy little vertex down here, just kind of hanging out. He's kind of controlling the whole thing. Hey, to the right, go this way. Hey, to the left, go that way. So then my answer then would be, okay, x is equal to, look, I did it again. X is equal to 0.7 and 5.3. But how would you do that out of a table? Okay, look in the table. Here's what I'm looking for in the table. If you didn't have a graph. Well, okay, x is 0, 1, 2, 3, 4, 5, 6. These are fine. But these are the y values. What I want to know is where is y equal to 0? Well, I don't have a y value anywhere through there that equals 0. But I do have a place where it goes from a positive to a negative. Do you see the sign change there on that one? Positive 4 to negative 1. Doesn't there have to be a 0 between there? If you took your pencil mark and you started on positive 4, just on a number line, and then you had to go to the left to go to negative 1, but you didn't pick up your pencil point and you just drew like, wouldn't your pencil point have to cross 0 at some spot? Yes, it would. So the question then is, where is 0 on this? Well, it's somewhere between x is 0 and x of 1. Where is it closer? Wouldn't it be kind of closer to 0 over here by negative 1 than 4 if it's evenly spaced? So shouldn't my x value be somewhat closer to 1 than closer to 0? And so that's where I get like maybe this one right here, 0.7. But where does it change sign again? Here's a negative, still negative, still negative, still negative, still negative. Now it's positive. Oh, it switched signs again. So it must have crossed 0 again in order to switch signs. Where is it closer to 0? Negative 1 or positive 4? I would say it's closer to 0 at negative 1. So your 0 is going to be closer than to 5. Something close to 5. Maybe 5.3. Maybe it's 5.2. Okay, but this is all an estimation. In a later lesson, we'll do how to do exact answers, but you should be able to now go through a graph and spot it and figure out what it's between, okay? And then in a table and figure out what it's between. And let's go back up and make sure that we understand we've asked the question. Oh, it didn't say estimate. It said if exact roots can't be found, state the consecutive integers. Aha. So x must be between, what did we say, 0 and 1, and between 5 and 6. Since I have a y value of 0 between here and here, the x values has to be between here and here. Somewhere between 0 and 1 for that first one, and somewhere between 5 and 6 for the second one. Okay. Now, that's a highly useful skill, being able to read in between data points. And there's a special word for that. It's not in the book, but I'll give it to you. It's called interpolation. My P got a bit sloppy there. Interpolation. Interpolation is reading between data points. Going beyond data points is extrapolation, but I won't write that down. Let me say that for a later time. Okay, is that it? Yeah, we're now on to the exercises. Okay, so what did we do today? We did quadratics in general form. Talked about ax squared plus bx plus c. We then talked about graphing by finding a vertex, finding y-intercepts, and then using the axis of symmetry to find some other points and plot some points around the vertex. It opens up if the a value is positive and down if the a value is negative. Maximums and minimums always occur at the vertex. So if you ever are asked a question, what's the maximum or what's the minimum? You know that you need to find something at the vertex. And then estimating, being able to read between integer or whole number values for roots. Yeah, it's good stuff. Quadratics is going to be good. I'm going to hold off on some more thoughts on quadratics. Got to save it for some later videos. But I hope you have a great day. God bless. Bye-bye.